Welcome back, my wonderful Allen High School students. We're winding down. We should only have two more videos or a couple more videos in our series on chemical reactions. This next one that we're going to be doing, we will cover in more detail next semester, but I want us to revisit acid-base chemistry, at least in terms of acid-base reactions. Now, we're going to be looking at neutralizations, either fully neutralized or partially neutralized. These are not redox reactions, and in fact, they're a subset of double replacement reactions. Now, typically, especially if it's a fully neutralized system, you're going to get a salt and water, a salt being just an ionic compound. Now, for the sake of refreshing our memory, an acid donates H+, and a base accepts H+. So really in these reactions, all we're doing is having this kind of tug of war with a proton. All right, so let's look at the first one here. We have hydrogen sulfide gas, smells like rotten eggs, H2S gas, bubbling through a solution of, so I want to add a plus there, not an arrow, sorry about that, bubbling through a solution of excess. That's how we know it's going to be fully neutralized. Potassium hydroxide. Okay, so again, it's much like our double replacement. We have an H+, the sulfide's -2, potassium's +1, hydroxide's -1. Remember, cations always dance with anions. So the H+ is going to go with the OH-, and that will give us H2O. The sulfide will go with the potassium, so we'd get K2S. And then we would need to balance that. It's completely neutralized, which means we neutralized all of the acid, and we get our water and we get our salt. Since this is a gas, plus it's weak, so on both fronts, we're going to keep that together. All group 1s are soluble, plus potassium hydroxide is a strong base. Notice that 2 gives us 2 potassiums and 2 hydroxides when we dissociate. Water is a molecular substance. We do not dissociate it. Group 1s are soluble, so I'm going to get potassium, and then I'm going to get sulfide. Now, when we look through here, we want to find our spectator ions. So those are ions that are identical on both sides. So that means we could have used sodium hydroxide or calcium hydroxide, anything to bring the hydroxide. It didn't necessarily have to be potassium. All the potassium did is drive hydroxide to the party. And then we'll get 2 waters plus that sulfide ion, and potassium was our spectator. All right? So double replacement, not much different. It's just that exchange of the H+. The H+ went from the H2S to the hydroxide. So the hydroxide was our base and the H2S was our acid. Now let's take a look at a partially neutralized. This would really lead us into a stoichiometry reaction. So let's first write the equation, or our reactants to start with. We have sodium hydroxide, solution of means it's aqueous, and carbonic acid. Acids are always aqueous. Now, what's different about this one? Well, this one says that I have 25 milliliters of a 0.1 molar solution of sodium hydroxide. Okay, and that's the same molarity that I have of carbonic acid. So what that means is I have equal moles of both of those, right? Because volume times molarity is moles. So I'd have 0.025 times 0.1 of both of them. So I have 0.0025 moles of each of them. In other words, I'm reacting them in a 1-to-1 mole ratio. that means I only have one hydroxide available to react. If I only have one hydroxide, it can only accept one of the H pluses. So I'll only get one water. I've replaced one of the H pluses with sodium. The other H plus is still there, and then I have CO3. That's sodium bicarbonate or baking soda. Right. So then I would have hydroxide. Whoops, I'm getting ahead of myself here. Since I'm forced to write these in a 1-to-1 ratio, I'd have one sodium ion, one hydroxide, plus one H2CO3. It's weak. I'm going to keep it together. And H2O. All sodium salts are soluble, so I'm going to dissociate that. And I get HCO3 negative, right? Because carbonate is -2. You add an H plus to that, and I have a -1 left over. So that's just a C there, right? And again, not surprisingly, alkali metals tend to be spectators. So it could have been potassium hydroxide. They could both do it. The key is the way the question is written is it forces us to keep these in a 1-to-1 mole ratio. Okay, and there we go. And sodium ion was our spectator ion. So there's some other nuances with acids and bases and acid-base reactions, but I think that gives us a good introduction and a good refresher of what acids and bases are at the same time. So until I get to work on these with you in class, this is, as always, signing off.